Welcome everyone to Module 3 on our Battery Management System course. In these sessions, we will explore a fundamental aspect of every battery management system, that is the battery estimations and the cell balancing. Throughout this module, we will understand the methods and the technologies that are used to estimate the key battery parameters, such as the state of health, the state of charge, the state of power, and we will also discuss how balancing methods will help to maintain uniform performance across the battery cells in our packs. So before diving into the details, let's take a closer look at these module sections and the agenda of this module. We will cover three key topics that are going to be essential for understanding the battery management system. At first, we will explore the various methods that are used to estimate the critical battery parameters, such as the SOC, S of health, and state of power, as well mentioned. Then we will see how the batteries naturally degrades over time and how that degradation will affect their capacity and their efficiency. And we will examine the different factors that contribute to agents, such as, for instance, the charge cycles, the temperature, and the operational conditions. And we will discuss also some ways to mitigate their impact. And finally, as we know, over time the cells will degrade, and the differences between the individual cells in the battery pack can lead to imbalances, and this reduce the overall performance. In the last section, we will review the different techniques that are used for balancing. We will explore the passive and active balancing and how these techniques are going to be used to equalize the cell charge levels and extend the battery lifetime. So now let's move to our first topic, that are the battery estimations. Estimation of the key parameters in the battery allow us to understand the current state of our battery better, and also to predict how it will behave in the future and what is going to be the future performance of this system. In the BMS, the estimations are going to be used, and we're going to estimate these four essential parameters that we already discussed in the introduction, and we explained a little bit what they were, but here we will see exactly what are the technologies used for determining these four parameters. So the first one is the state of health, and the state of health is a parameter that reflects the overall condition of the battery, and it will indicate how much energy do we have in comparison to the original capacity, and it will help us to determine whether a battery is still fit for use or if it needs, for instance, to be replaced. Then we have the state of charge, and this indicates the remaining energy in a battery as a percentage of its full capacity. And this parameter will guide the user to know when to charge and when to discharge the battery, and how to optimize the performance to prevent, for instance, over discharging it. Next to it, and very close to the definition of the state of charge, we have the depth of discharge, that represents the percentage of the battery capacity that has been already be used relatively to its fuel charge. And it is important because managing the depth of discharge will help us also to prolong the battery lifespan, as will be explained later on. And there is another term that is estimated in the battery, that is the state of power. And the state of power will measure the maximum power that a battery can deliver under specific conditions, such as, for instance, temperature, load, and degradation. And this parameter is particularly important in high power systems like electric vehicles, where we need to know exactly what is the power that the system can deliver and how it's going to be limited depending on the conditions, current conditions of our system. So in general, The BMS will use a combination of the sensing circuits and also computational methods to achieve all of these different estimations, and we will detail in the upcoming slides how each of these parameters is estimated and what are the algorithms and the methods that are used currently in the BMS. And before doing that, maybe we will explore one of the key components that is responsible for doing all of these estimations in the battery system, and this is the fuel gauge. The fuel gauge is going to be a subsystem in our BMS. It can be either an electronic component or a component that is integrated in the firmware of the BMS. And the fuel gauge basically integrates all the information from the sensors and the algorithms to be able to provide real-time data estimation of the battery conditions. So it will combine and it will collect the information from the current sensing and measurements from the current flow in the current that is flowing in and out of the battery, and this will be used to track the charge and discharge cycles of our battery accurately. It will always continuously check the battery voltage and access to this information to know the overall charge level and the overall health of the battery. And also it will combine estimations like the Coulomb counting or module-based estimations to be able to calculate the state of charge, the state of health, and the remaining battery life with high accuracy. The fuel gauge integrates all of the data and provides a comprehensive overview of the battery status, and this helps us to make informed decisions about how to use and how to maintain our system. The fuel gauge, for instance, in order to accurately estimate the battery parameters, will need to be selected based on the applications, the available resources, and the requirements. Different estimation techniques are gonna be evaluated then, and they're gonna be selected depending on those application requirements. In order to compare them in the following slides, we will use these key parameters and we will see how these parameters will influence the effectiveness of the estimation. So let's go through each of these parameters, starting with the accuracy. And the accuracy, this parameter refers to the precision of the state of charge and or the precision of other estimations, and how precise it is under different operating conditions. High accuracy is going to be critical in applications like electric vehicle, for instance, or energy storage systems, where the performance is optimized based on that information, and that information is going to be essential, for instance, to determine what is the range of the vehicle and how many, for instance, kilometers we can drive extra with the current state of charge that our battery has. Another parameter that we will assess is the ease of the implementation. So some estimation techniques will require complex algorithms and complex sensors, while some others are way much simpler to implement. The choice of the technique will depend on the system cost and the complexity of the system and the expertise that is going to be required to deploy and to implement these algorithms. Then we have the real-time capability, and this is going to be the ability that the algorithm has to provide real-time updates of the battery status. And this is going to be especially important in applications that will require dynamic power management, and where we need to know at any time what is the current capacity and what is the current power that we have available for the system. In this case, techniques that have faster response times are going to be preferred in the systems that then will require the immediate action, and however those are usually also that will require also more complex algorithms, and they are not going to be as easy to implement. And then we also have the dynamic adaptability of the different techniques. And this is going to measure basically what is the effectiveness of the estimation methods in handling different conditions. For instance, how dynamically it adapts for different loads that are going to be changing over time, even very quickly, how it's going to react to different temperature fluctuations in our battery, and how it adapts to the battery aging of our system. An adaptable method can adjust all of these variations and provide reliable estimations over time, even if the conditions of the battery are changing from one cycle to another. And the last one is going to be the cost effectiveness. This is how we overall measure the affordability of the techniques, and considering here both the hardware that is required for performing the estimations and for getting the measurements of the battery, but also the software requirements. So some highly accurate methods can in some applications not be practical because they are going to be very cost sensitive and do not make sense to include them, for instance, in low-cost applications. In general, a combination of the estimation techniques is often used in the modern BMS, and here what we are doing is to achieve, for instance, improved reliability, whilst we are trying to balance the trade-off between the accuracy, the cost, and the real-time operation, and all of that will influence the decision of what technique do we implement in our system. So let's start with the state of charge estimation, and let's remember its definition. So as it was said before, the state of charge will represent the percentage of the battery that the percentage of the capacity of a battery that is available, and this is going to be relative to its full maximum usable capacity. This type of information will provide us real-time data of the energy reserve of our battery, and this will help us, for instance, in planning operations such as to know the remaining range of operation of a vehicle, and to also know when the battery will be empty, or when it is recommended to discharge the battery to prolong its lifetime. This is the equation that is used to determine the state of charge, and here basically we state that the SOC is going to be equal to the available capacity in our system divided by the maximum usable capacity. And it does not take into account the capacity that the battery has lost due to degradation. It is very important to have accurate SOC estimations. Basically, it is going to be very important because the SOC helps us to understand how much charge is left in our vehicle, and this will ensure the usage and avoid, for instance, unexpected shutdowns in our system. Also, to have proper SOC estimations will prevent overcharging, and this leads to faster degradations in our battery. Also, it prevents deep discharging, and deep discharging can also reduce significantly the lifetime. So by knowing an accurate SOC level, we can keep the battery within the limits that prolongs the lifetime of the whole system. And also in some applications, such as the electric vehicles on renewable energy systems, the SOC is going to be crucial for managing the flows of energy and to optimize the efficiency not only of the battery but of the whole application. Despite of the importance and all the benefits that the SOC estimations brings to our applications, there are going to be also several challenges that are associated with these calculations. One of those is that over time the battery capacity decreases. That is the degradation that we are showing here in this figure, represented by the red shadow. And that degradation makes very difficult to predict accurately what is going to be the available charge accurately. And also temperature fluctuations in our system and the varying load conditions will impact the battery behavior and also will make even harder the estimations of the SOC accurately. Those are some of the challenges that the different algorithms needs to deal with to provide very accurate values of the SOC. So now let's explore some of the techniques that are used for this estimation, and let's start with one of the most simple ones, that is the calculation of the state of charge based on the open circuit voltage. This is one of the simplest and also one of the most widely used methods that are used to estimate the SOC. And here basically we are using the relationship between the charge level and the battery voltage when it is addressed, meaning that it is the voltage that we measure when there is no current flowing in or out of the battery. In this case, by calibrating the voltage measurements against the SOC values, so by doing an initial characterization and correlating the voltage measurements with the SOC values, we can develop this algorithm that allows us to have a real-time estimation when the battery do not have current flowing through this. How do we implement this type of algorithm then? So first of all, the battery must be left idle for a specific time. It means that it has to be in a stable open circuit voltage. Once we have the battery already relaxed, we take the measurements of the voltage, and that measurement has to come with high precisions, since the voltage readings and the battery temperature is going to be dependent of the battery temperature. So we need to be sure that that measurement, for instance, and the sensing voltage network that we are using is as stable as possible, even in variable temperature conditions. Once we have the value of the open circuit voltage, then we can use different lookup tables or equations that will correlate both parameters. In that way, we can obtain the related state of charge. This here, for instance, shows one of the figures of this type of curve that we can use to correlate the voltage that we are measuring with the equivalent SOC. And as you can see, this type of curve usually are measured at different temperatures, and you can see that there are differences or small differences as a function of the temperature in the system. Some of the advantages of this method is that it's very simple, so it requires minimal hardware and it can be easily implemented in almost any battery management system. It is also no complex, so it requires low computational resources. It has very high processing power. It does not require neither high processing power, so it makes it very cost effective. Also, it is very easy to implement these lookup tables or functions that are already characterized here. And due to its simplicity, it is an economical choice for applications that require basic SOC estimations. This simplicity has, on the other side, some limitations and some disadvantages. One is that the voltage readings may vary with the temperature, and as the battery ages, those initial characterizations will lose precision, and this will lead to potential inaccuracies in the measurements. Also, the battery voltage characteristics will change with the temperature, and that will affect the estimation. And also, this is a method that requires that the battery has to be relaxed in order to get accurate readings. And it's not always practically to have the battery relaxed and to only be able to capture the SOC value once the battery is relaxed. So in some applications that requires, for instance, or that has very dynamic behaviors, like the electric vehicles, that usually there is going to be a load to the battery, it is not practical, this estimation. And finally, as we know, as the battery ages, their voltage profile will change, and also this will reduce the general effectiveness of these methods. Despite of this, the OCV method is still one of the most useful methods in applications that do not require real-time operation, or where this is not critical, and also where the cost is one of the major factors, and where we have low computational resources. Next, we will discuss then the column counting methods, and this, unlike the open circuit voltage, the column method, in this case we rely on the measurement of the current that is flowing in and out of our battery, and we are using that current, the value of the current, to track the changes in the charge dynamically. The Coulomb counting methods will estimate the state of charge by integrating the measured current over time, and in this way it tracks the charge that it is going to be added during charging, and it is going to be subtracted during discharging, and like this we can determine what is the remaining capacity that the battery has. Mathematically, it is expressed with this equation that is shown over here, and let's take a moment then to break down the column counting equations step by step, and in this way we can easier understand how it works. So how we can read this equation. So at the left side of the equation we have the state of charge that basically represents the value that we are going to calculate at a given time, and it will tell us how much energy and how much charge is remaining on our battery. This is going to be equal to the initial state of charge of our battery, and this is the known starting value of the battery charge at the beginning of the measurement. So once we start, we need to take assume an initial value in the state of charge. Usually we discharge completely the battery, we assume that the SOC is 0, and we start then our calculation of our measurement. So think of this as the fuel level in a gas tank before even starting a journey, and it is what it is at the beginning. The initial state of charge is then we subtract 1 divided the battery capacity multiplied by this integral, and this 1 divided the battery capacity that is represented by the letter Q is a term that we use in order to have the charge flow normalized relatively to the full capacity of our battery. So Q is a constant, and this represents the fuel capacity of the battery pack when it is new. And then we have the multiplication of this with the integral that is going from 0 to the time t, and this is going to be the integral of the current, and this part basically will sum up the current that is flowing in and out of the battery over time, starting from the time 0 to the current time that is t. Basically, if more current flows out than in, the SOC will increase, and in the opposite, the SOC will decrease. The Coulomb counting method is implemented with several processes, but to summarize it, basically we start with the measurement of the current, and we have a current sensor that is placed in series with the battery, and that will continuously measure the charge and the discharge currents of the battery. Then we use numerical techniques to calculate the integral of the current over time. For instance, we can use discrete summation, as you are showing here, and in that way we can calculate the current and accumulate the current to be able to estimate the total charge flow and to perform the calculation of the integral that is over here. And once we have this, we can accurately estimate the SOC that is required based on the initial SOC level using this equation. Maybe here also to note that besides of the current measurement and the integration of the current, in order to have accurately estimations, in some cases, very often we will require the calibration, and this involves, for instance, fully charging and discharging our battery under controlled conditions to be able to determine its capacity under known conditions and to be sure that we are not adding errors in our measurements. Some of the advantages of this Coulomb counting method is that it provides a very precise representation and calculation of the charge that is in our battery. It requires only a current sensor, and it can be straightforward integrated in the algorithms, and also it is very effective in applications that are having that requires continuous monitoring of the energy. The disadvantage is that usually we can easily integrate errors, so small inaccuracies in the current measurements will accumulate over time because we are integrating that, and if we don't do the calibrations, it will lead to significant error estimations in our systems. Also, it does not measure charge loss. So if you remember the equations, it depends of the factor that where we take the integral and we divide it in the total capacity of the battery. And if that capacity degrades over time, it is in this method not possible to estimate that degradation. So it do not consider self-discharge, parasitic loss, temperature effects that will change the total capacity. And finally, it also depends on the initial state of charge of our battery that is not accurately known in all of the times, and because of that, the entire estimation process may be unreliable if we don't have a precise initial state of charge calculation. Another method then is, for instance, the model-based methods. These are more advanced approaches for estimating the state of charge. And in these methods, what we are going to do is to use mathematical models to simulate the electrochemical behavior of our battery and to enhance in that way the accuracy and the reliability of the model. In this case, we will estimate the SOC by accounting on different parameters of the battery, for instance, on their internal resistance, their capacity, and also modeling already the aging effects. Here we are showing one of the models that is it's a model that represents already the internal resistance, the dynamics of the battery, and also the agings with the self-discharge current of the battery. These models in general involve a lot of different steps. For instance, at the beginning we have to create the mathematical model and to have initial characterization of the model with, for instance, this type of equivalent circuit models, and to develop this to represent as close as possible our battery system. Then we need to find each of these parameters, such as the resistance, the capacity, and so on. And all of this is derived from experimental data and from the continuous experimentation with our system. The more we have experienced our system, the more accurate these parameters would be. And then we have to run these estimations with the specific algorithms, and comparing those measures with the predictions of our models. And finally, in the systems, to adjust those estimations based on the parameters of the sensors and the input of the sensors, such as the current, the voltage, and the temperature. Some of the advantages of the model-based techniques is that they are very accurate even under varying conditions, non-linear operations, and even in the presence of different frequency temperatures, because all of this is already modeled in our system. It performs well in a wide range of applications, from electric vehicles to grid storage applications. However, it requires advanced computational resources, and also it requires a lot of expertise in the system modeling and in the algorithms development for running this. It also requires frequent calibrations to maintain the accuracy, and the implementation of it is way more expensive compared to the simpler estimation methods that were presented before. Related to the state of charge, we also have the depth of discharge, and here, as it was mentioned, this is the percentage of the battery capacity that has been used already. So if we have a battery with a state of charge of 70%, the depth of discharge will be 100 minus 70, it will be equal to 30%. Understanding and managing the depth of discharge is going to be very important for several reasons, because it helps us to determine the usable capacity, and also to know it's going to be related directly with the impact on the battery lifetime. But in the estimation, the calculation is quite straightforward, because as you see here, it is just this formula that can be easily implemented once we have already estimated the state of charge of the battery. To compare and to know the difference between the depth of discharge and the state of health, we need to know that the state of charge will focus on how much charge is remaining in the battery, while the depth of discharge will provide us a clear picture of how much energy has been already used in the battery. That's the main difference between both of us. And understanding both parameters is going to be very important for better monitoring the battery and managing the system. Now let's jump to another critical parameter in the battery management system, that it is the state of health. And the state of health will provide us insights of the overall condition of the remaining useful life and of the battery, and how it compares to the original capacity and the original performance of the battery. So the state of health is an indicator of how much battery has degraded over time, and it's typically expressed as a percentage of its original capacity. So in this case, a battery that is new will have a state of health of 100%, and usually we consider that the battery is still in good condition if the state of health is above 80%. Below that value, the battery may no longer meet the operational requirements for its initial purposes, and because of that it needs to be replaced. It is important to know that it doesn't mean that the battery cannot store energy anymore, or that it's condemned to fail. When the battery has a state of health lower than 80%, it means that it cannot store energy as efficiently as before, but for instance it can be used in other applications. If the initial purpose of the battery was to be used in electric vehicle, maybe for an electric vehicle the range of 80% is not longer acceptable, but we can take that battery and use it in another application, like an energy storage system, where we can continue use the battery and recycle this battery. To have accurate state of health estimations is going to be very important for several reasons. One of those is because monitoring the state of health will help us to prevent unexpected failures in our battery, and all of those could lead to safety hazards, and this is very important, especially in applications such as electric vehicles or medical applications where safety is critical. Also, by tracking the battery health, we can, for instance, perform maintenance and to schedule those maintenance in an optimized way, reducing the downtime of our system and reducing the operational costs that are going to be related to that. And also, to know the state of health, which allows the users to plan the battery replacements very strategically and to avoid unnecessary costs of replacements when it is too late. The main factors that affect the battery health are very important, because those are the factors that we need to try to predict in our battery systems and in our algorithms that predict the state of health. So we have first the capacity degradation, and this is how the battery loses its ability to hold charge over time. Then we will also have the internal resistance. As the battery degrades, the internal resistance of the battery increases, and this will lead to higher energy losses and to reduce efficiency. So this is another parameter that we usually have to track. And finally, we also need to track the efficiency reduction over time. So older batteries will experience longer charge time and reduce the capacity of delivering power, so it will have a reduced power output, and all of this will impact the overall system performance. So how the state of health is estimated. And here there are broadly classified into categories. The methods that we are used can be experimental or can be model-based. The experimental models will involve conducting control tests to gather the data and to correlate the battery operation parameters with its health conditions. And these methods are based on direct measurements or indirect measurements. So in the direct measurements, for instance, we will rely on physical measurements on our battery, like for example, if we measure directly what is the internal resistance of our battery and we monitor the increment in the internal resistance, we can over time also detect the degradation of the battery. So in that case, we are directly measuring one parameter. Or if we measure directly the capacity, and we can do these fully charge and discharge cycles under very controlled conditions, we can also measure the available energy in our battery and to track it when it has been degraded. So these methods are very accurate, but typically are performed in laboratory conditions where we can directly, when we have access to the physical parameters of the battery. On the other side, we have the indirect methods, and these methods will estimate the state of health based on correlated parameters without having the direct measurements on the battery. So for example, we can use some of the methods that we discussed before to correlate the open circuit voltage with the state of health, or to have the Coulomb counting tracking the charge and the discharge cycles to assess the degradation. So these methods are easier to implement, but are lower or that have a worse accuracy compared to the direct methods. And on the other side, we have the model-based methods. And the model-based methods will utilize and will use these mathematical models to estimate the state of health by interpreting all the battery behavior under different battery conditions. So these type of methods will use real-time data, and also will use historical data to be able to estimate the state of health, and we can divide it in two. First, we have the data-driven models. And the data-driven models will use, for instance, machine learning, or it will use, for instance, statistical techniques and statistical analysis to predict the SOH, and this can be done by analyzing the historical performance data of our battery and from other batteries that are very similar to the one that we have. We have, for instance, here neural networks that we can include, or regression analysis that are very complex that we can use in this data-driven model. And also we have these adaptive algorithms, and this type of algorithms basically continuously update themselves and learn from themselves based on the real-time data and improve the estimation accuracy over time using for instance, Kalman filters or particle filters that help us to handle very complex battery behavior and no linearities of the batteries, as well as combining, for instance, measurement data with model prediction, and to include all of that in very complex algorithms that can predict the batteries. This, I think I already explained it a little bit, so I will go a little bit faster to this. But basically, in the direct methods, as I mentioned, we can estimate based on the internal resistance, and this is the opposition that the battery, the battery will have to the flow of current, and as the battery undergoes repeated charge and discharge cycles, the chemical and the physical changes inside of the cells will cause the internal resistance to rise. And some of the methods that we can use to calculate this internal resistance is for example, to use short current pulses. In this case, we apply to the battery a very brief pulse of current, and then we see what is the voltage response of this that we receive. That voltage response is analyzed, and in such a way we can determine what is the precision, what is the resistance. Also, there is some specialized instrumentation and devices that can measure the resistance with even some micro ohms and precision. That is very good. This is laboratory equipment. And finally, by analyzing the heat dissipation in our battery, we can infer what is the internal resistance, as the heat that is related will correlate with its internal resistance. And the other direct method for estimating the state of health is the measurement of the capacity. And here, what we have to do is to fully charge the battery under controlled conditions, and then fully discharge it at a constant current until it reaches its cutoff voltage. All of those very precise conditions. And the energy that is being obtained during the discharge is being measured, and it is compared then with the battery original rated capacity. But as mentioned, both of those are very used in experimental conditions. It's not very common to use them in systems that are under operation. In the indirect methods, then we also have the open circuit voltage and the Coulomb counter, and both of those are have been already explained. But we can correlate here the open circuit voltage with the state of health, but with the state of charge. But as you can see, we can also have different of these curves, at different state of health, and in this way we can correlate also the value of these parameters, but the accuracy is not very high. And to use the Coulomb counter also to calculate the remaining capacity by integrating the measured current over time, and to compare it with the initial condition is also another possibility. And also, finally, there are these base model techniques, and as I mentioned before, here what we are trying is to use the historical data and the real-time data to train predictive models based on machine learning, statistical models, and to have all of these analyses to have very accurate values of that. And in the adaptive algorithms, basically the algorithm will continuously adjust the model parameters based on the real-time data condition, and it will learn from the parameters and from the data that the battery is obtained to improve the accuracy also. And here are some examples, and the loop where we predict, we correlate, and also we recalculate our model parameters based on that. And finally, the last of our parameters is going to be the state of power. And the state of power, it's a very important parameter to estimate within our battery, because it will help us to evaluate the ability of the battery to deliver power under very specified conditions, such as, for instance, the different load demands that we may have at the different temperatures, at the different state of charge, and so on. So the SOP is particularly important in applications where the power delivery is going to be critical, such as in the electric vehicles or the energy storage, or in industrial applications. This will represent the maximum instantaneous power that the battery can supply at a given moment. So depending on the state of charge and depending on the state of health of our battery, the amount of power that we can deliver can be limited. So the SOP will help us to determine whether the battery can meet the demands of high power applications without exceeding the safety limits, or if it is required to limit the power and it will not be possible. It is expressed mathematically with these equations. In these equations, the maximum power, it is gonna be the highest power output that the battery can provide under optimal conditions, and the nominal power is the expected power output that the battery can provide under normal operating conditions, and the relation between both of them will give us the state of power estimation. This parameter is gonna be important for different reasons. One of those is that evaluating the performance in the battery based on the SOP will help us determine in an electric vehicle, for instance, the acceleration performance of the vehicle, the limitation in the acceleration that we may have, and the peak power delivery capabilities that we may have. That is in the case of an electric vehicles, but in a case of a renewable energy system, it will help us to ensure that the power that is available during, for instance, peak demand times can be supplied. Also, this will help us in general to design the systems and to be sure that the system that we are designing will handle high power demands without overloading the battery and without affecting the safety of the battery. And it will also ensure that the battery will operate again within the safety limits to avoid overheating and to avoid any potential discharge or over discharge or overcharge failures. There are two common methods that are used to estimate the state of power. First, we have this hybrid pulse power characteristic, and this is one of the tests that we can do. And in this method, a series of current pulses of varying amplitudes and durations are applied to the battery, And for each of these pulses in this pulse train, we analyze the voltage response of our battery and help us to determine the battery resistance, and the power capability will be related to that resistance. A battery that has a higher internal resistance will have a lower power capability because it will generate more heat, and it will be less efficient than a battery that has a low internal resistance. And also we can use the SOC calculation to estimate the SOP. In this case, we can have models that relate the state of charge with the internal resistance, and to predict, for instance, that as the state of charge decreases, the available power will also be reduced, and to use this to estimate the value of the state of power.